All right, everyone. In this video, we are going to take a first look at even greater integrals, that's integrals over larger dimensional domains. And we're going to be looking at this specifically for triple integrals. And in this video, triple integrals over a box domain or a rectangular prism domain, just thinking of that as a 3D box. This will generalize what we've seen with double integrals, and it's not a great stretch of the imagination to see that once we have generalized from two-dimensional double integrals to three-dimensional triple integrals, we could continue to generalize this as well. So the very first thing that we need to do is just make sure that we standardize some notation and some ideas about what our domains even look like. So before I get to my multivariable function, let's talk about our domain. And in 3 dimensions, our domain should be three-dimensional, so it should have an x, y, and z coordinate. And I have 2 different but equivalent notations written up here for my domain, which I'm calling D. And so our domain D is, you could think of it as the set of all, I'll look at this notation first. This is the set of all points in three-dimensional space, so the set of all triples, x, comma, y, comma, z, such that the x-coordinate is between 2 numbers a and b, the y-coordinate is between 2 numbers c and d, and the z-coordinate is between 2 numbers e and f. So that is one way that we could write this box domain. But another way that we could write it, and possibly a slightly more useful way to write it, is using our Cartesian product notation as we see up here. So this is like the x interval from a to b. So these are our x values. And we're going to Cartesian product that with the y values, the interval from c to d. And then we're going to Cartesian product that with our z values from e to f. So the x values are between a and b, the y values are between c and d, and the z values are between e and f. Okay, cool. So how do we visualize this? Well, if I'm thinking about this in three-dimensional space, I might have a picture that kind of looks like, or at least it's beginning to look like, the picture we have down below. I've identified the numbers A, B, C, D, and E, F on their respective axes. So again, the x-axis is the one that's coming out of the screen, the y-axis is the one off to the side, and the z-axis is the one that's pointing straight up. Much like with my two-dimensional domains, I'm taking my A to B and extending it perpendicular to my x-axis. I'm also taking C to D and extending them perpendicular to my y-axis. So what I see down here, it's similar to my two-dimensional rectangular region R that we've seen previously. And so I have that drawn down here in this region over here. However, our new three-dimensional domain is not just going to be sitting in the xy plane, it is in three-dimensional space. And so I think it is worth pointing out that what I just drew in black, that rectangle down there, is not really my 3D domain D. It is the shadow that D will end up casting down onto the xy plane. And so what I have here, this is just the shadow of this rectangular region D. And by shadow, I could also call that like a two-dimensional projection of D down into my xy plane. But I tend to think of it as a shadow, as if the light source was directly above D and it was casting it down. Now, we still need to give this a third dimension. And so notice I've identified my E and F along my Z axis. So what I really need is the 3D box whose shadow is D, but whose heights range from E to F. So whose heights range in that height there. And so the way that I might draw this is as follows. I might create a plane at the height of E. So this will be perpendicular to the XY plane. but it's at a height of e. And I might now take a look to see where my shadow of D, the shadow of D, you see I have these vertical dotted lines. I might see where that vertical dotted line, where each of those four vertical dotted lines intersect this plane. And so what I might see is that they end up doing it at these four different points here. Right? And so that larger plane that I had made, oh, there we go. That larger plane that I had made ends up intersecting it at these 4 points. And I realize I've actually drawn this point kind of poorly. It should have been down here. Okay, so we get something that kind of looks like this. Again, we had this larger plane E that I had drawn earlier. So this is like my Z equals E plane. But I'm just seeing where the height E intersects over the shadow of D, so where it hits those 4 points, and I've seen them there. Okay. Now, I'm going to do the same thing up here at a height of F. So I'll take a plane at a height of F, something like that, and intersect those vertical lines and see where those are. And what we'll see is that there are 4 more points, maybe here, 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 and here, or something like that. And then we'll end up drawing or connecting those together. And in doing this, we've really got our box. It's starting to come together. So again, this box, it has its upper, you'll notice that like any rectangular box, it is composed of these 6 different sides, and each of these sides corresponds to a given height, a given plane. So this top side, this top was the height of Z equals F, and this bottom corresponded with Z equals E. And so we could list if we wanted all 6 sides, and maybe I'll actually do that. It's a fun exercise, and I have the space in the lower right. So we've got our top side, that corresponds to Z equals F. The bottom side corresponds to the plane Z equals E. And then we've also got, let me see what I can do here as far as color coding goes. We've got the front, from our perspective, the front face. That is going to be, I'll erase this to keep it relatively clean, but that's this face right here, so the face that is closest to us, the viewer. And notice that aligns with the plane that corresponds to x equals b. So that's a vertical plane slicing off the front of that box. And so the front side here corresponds to x equals b, while the back, from our perspective, corresponds to x equals a. And again, just looking at the back, that is this vertical piece right here. Okay. Finally, we've got our left and our right sides. So the right side, right, that's going to be this one over here. And that corresponds to the vertical plane at y equals d. So that's the y equals d plane. And then the left is going to be the y equals c plane. And that's going to be this plane right. Oof. Man, I was doing so well up until that point. That's going to be that plane over there, the left-hand side. Okay, and this is the 3D box, sort of sectioned off by these 6 different planes that we've identified. And those 6 different planes will soon correspond to, as we'll see, bounds of integration if we try to set up a triple integral. I will also just point out, this is not that important right now, but it will be important down the road, that the shadow of D, the thing that we identified before, this still corresponds to a Cartesian product in two-dimensional space, and it has exactly these other bounds of integration over here, or these other boundaries, I should say, as well. So down the road, we will want to pay more attention not only to our 3D shape, but what shadow the 3D shape projects down onto the two-dimensional XY plane. Okay, cool. I love it. This is a fun picture. Let's see what we can do with this. So into the mix now, we have this three-dimensional domain. We're going to introduce a multivariable function of three variables. So I'm going to call this capital F of x, y, z, specifically calling it capital F so that I do not get confused with my lowercase f in the picture up above. So capital F of x, y, z is a multivariable function. It has three variables, and it has this boxy domain D as its domain. And so as long as this function is nice enough, we can think about a triple integral of f over d, giving us the notation that we see over here on the left. And I'll box this. So just like we've seen before, this is going to represent notation, triple integral over domain D. And this time, because it's a three-dimensional region, the D portion is dV for volume. You could imagine that as becoming a dx, dy, dz, or something similar. Now, we lose a little bit of intuition about what such an integral can represent. We've seen that a single integral can represent area, and a double integral can represent volume. So a triple integral, in a certain sense, represents some version of a four-dimensional volume. But us being three-dimensional beings have a lot of trouble intuiting what that might mean. But we can talk about examples or applications of triple integrals down the road. And for now, we'll just see this as something that we can compute, giving us some sense of four-dimensional signed accumulated volume, right? Exact meaning to be teased out later. But what we have here is that similar to double integrals, this triple integral can become an iterated integral in which I calculate a calc1 integral three different times, working from the inside out. And so this is a generalized version of Fubini's theorem. And let's see what this looks like. So our triple integral can be computed as three single integrals. On the inside here, we're going to start by integrating our z values. So this is an integral as z goes from e to f, lowercase e, lowercase f. Those are our bounds there. And we're going to integrate our triple integral dz. In doing this, we're going to eliminate any z's in our function. We'll do that by finding an appropriate antiderivative and plugging in using the fundamental theorem of calculus. So in that process, we'll eliminate any z's, and what is left is just a function of x and y. We are then going to turn to the next integral, so it just has x's and y's. We are going to focus on this step, and this step is going to be an integral as y goes from c to d. Whoops, y goes from c to d, so those are our y values. And we're going to integrate that dy. In doing so, we'll find an antiderivative. We'll plug in y equals d minus plugging in what we get for y equals c. Again, just using the regular fundamental theorem of calculus. We'll plug in for all of our y's. We'll run out of y's. And then the result is just something involving x's. And then in the end, we can integrate that x expression as x goes from a to b. All right, and this is going to give us our process for computing higher dimensional integrals over these more complicated higher dimensional domains. I'll conclude this video just by working through one explicit example. So we have an example recorded. I'll scroll down here. All right. And so we are going to compute the integral of this function over this domain D. And so let's see if we can set this up. So it's going to be a triple integral. The function is x plus 4yz. And then we can integrate that dx, dy, dz. I should have said earlier, let me scroll up just very quickly. I should have said earlier, the way that I wrote this, it was dz, dy, dx. But in the true spirit of Fubini's theorem, I can put this in any order that I want. So I can integrate, in this case, it was dz, dy, dx. I could integrate dx, dy, dz, dy, dz, dx, etc. You understand. So I could integrate this next expression in any order that I want. And I think no matter what, we'll end up at the same answer. Let me go ahead and integrate my x's on the inside. So these are my x coordinates. And so I'll integrate as x goes from 0 to 1, and I'll integrate that dx. Then I'll go ahead and integrate my dy. So I'll just go in the order that it's written here. So that's going to be y goes from 0 to 2. And I'll integrate dy. And then finally, I'll integrate as z goes from 1 to 4. So I'll integrate dz. I did not have to choose this order. I'm just doing that spur of the moment because that's the way it's written. But we could really choose any order that we wanted. Okay, so let's go ahead and give this a go. And so my outer integrals are going to stay the same from 1 to 4 and from 0 to 2. But on the inside, in order to compute this integral, I need to find an antiderivative. And I can do this using the fundamental theorem of calculus. And my variable is an x. So my x becomes an x squared over 2 plus, and now notice the 4yz doesn't have any x's in it. So that just becomes a 4yz times x, right? The same way that any constant, when integrated with respect to x, would become a constant times x. I should say that is my antiderivative, but I want to evaluate this as x goes from 0 to 1. I'm going to finish doing the stuff in the parentheses. And when I do that, I will have eliminated all of my x's, and I will just have a dy dz expression to compute. All right, let's keep going. Right, the fundamental theorem of calculus said I needed to find an antiderivative and I needed to plug it in. So let's go ahead and plug in. When I plug in x equals 1, I'm going to get 1/2 plus 4yz times 1. And then minus, so that's what I got first, minus when I plug in 0, I'm just going to get 0 plus 0. Lucky me. So everything simplifies down. Notice I have no more x's. I've integrated them all away. And so my expression just involves y's and z's, which is great because I'm now just integrating dy dz. Okay, let's go on to the next one. So now I can focus on my y. I'll keep my z expression out here. So integral from z equals 1 to z equals 4. But at this point, I'm going to want to integrate the expression 1/2 plus 4yz, and I'm going to want to integrate that dy. So I'll do that in the purple parentheses. So 1/2 plus 4yz I need to find an antiderivative of that with respect to y. And so the 1/2 will just become a 1/2 times y plus, and then the 4yz, well, the 4 will stay a 4, the z will stay a z, but the y will become a y squared divided by 2. That's because I'm integrating dy. So I found an antiderivative for what I had with respect to the y variable. And now I need to plug in at y equals 0 and at y equals 2. Okay, so still in parentheses here. When I plug in y equals 2, I'm going to get 1/2 times 2 plus 4 times z times 2 squared. So that's 4 times z times 4 divided by 2. So I think that's just 8z when the dust settles. And that's my first half minus my second half. That's when I'm plugging in y equals 0. And so I will, again, just get 0 plus 0 there. All right, and notice in doing this, I have eliminated all of my y's. I plugged in y equals 2, and I plugged in y equals 0. And so there are no more y's left. The only variable still floating around is a z variable. And that's great because I am trying to now integrate as z goes from 1 to 4, and I'm integrating dz. All right, the end is in sight. I'm going to rewrite this, actually, just to make it a little bit neater. So again, we're just integrating as z goes from 1 to 4. We have the expression 1/2 times 2, so we're integrating the function 1 plus 8z, and we're integrating that dz. Okay, everything else disappeared. So by the fundamental theorem of calculus, I find an antiderivative. This is with respect to z. So the 1 becomes a 1z, and the 8 becomes the 8z becomes a 4z squared, right? That's 8z squared divided by 2. And I evaluate this as z goes from 1 to 4. When I plug in 4, I'm going to get 4 plus 4 times 4 times 4. So that's 4 plus 64 minus, and now when I plug in 1, I'm going to get 1 plus 4 times 1 times 1. So this is 68 minus 5. We get a final answer of 63. And so this is an example of us working through this entire process, starting with a function of 3 variables, integrating over a triple domain, but ultimately arriving at a single answer. That's going to do it for this video. Thanks so much for watching, and see you next time.